Okay, so here we go. We have a second order derivative being approximated by let's say some proportionality constant a. Let's put a question mark on this one. Times this is at k delta x. The average of wi minus 1 and wi plus 1 minus wi, right? Okay, so what is A? So here, you can actually do, one thing you have to decide when doing Taylor series analysis is what do you choose for x0? In this case, it actually doesn't matter for the final result what you choose as x0. You can set x0 to be, for example, I times delta x, or I plus 1 times delta x, or I minus 1 times delta x. It doesn't really matter. The final result you're going to get is the same. But what matters is how much arithmetic you have to go through to get the final result. You can even set x0 equal to I plus 2 times delta x. You can also get the same result. It's just you have to go through a lot more complicated calculations. So, for example, in this case, this is actually the one that turns out to have the least amount of calculation. So let's stick with it. Okay? So, first of all, let's represent Wi into Taylor series analysis. Wi is actually equal to W at x0. Only the first order, only the zeroth order term is going to be present over here actually. Because all the other terms is going to be, well, for example, let's just, for example, I think it's might be easier to just say it's Wx, right, as opposed to x1. So basically x you can change, and we have x minus x0 in all these terms. So imagine x is actually equal to x0, then all the terms other than the green one is actually equal to 0. So we don't have to do anything else here. The Taylor series analysis is trivial for that point. Wi plus 1 is less trivial. It's equal to Wx 0 plus delta x, right? It's 1 point to the right of x0. So that is represented as Wx0 plus the derivative, which here I have to use partial, at x0 times delta x, right? Plus half of second order derivative, delta x squared, plus etc. Let's just ignore all the later points for now. And we're going to see we will have to keep more points if we want to know more about the scheme. But for the purpose of determining A, let's just assume they are things that are at least proportional to delta x cubed. Well, I mean, there is actually a notation for this kind of thing that we know is at least proportional to delta x cubed. It's called a big O notation, big O delta x cubed. So when you say big O delta x cubed, it means a summation of terms that are proportional to delta x cubed, proportional to delta x to the fourth, proportional to delta x to the fifth, etc., etc. It can also include terms that are proportional to the delta x to the 3.5 or things like that, right? So that's all the terms belongs to this big O of delta x cubed. So that's our Taylor series for Wi plus 1. Wi minus 1 is very similar, but the location is different. Instead of plus delta x, we always have minus delta x. So we can basically copy what we have above, but everywhere we have delta x, we are going to substitute with minus delta x. Okay, plus this minus delta x. Well, things that are proportional to delta x cubed is also proportional to minus delta x cubed. So we'll just keep it over there. Okay, and with that, we can have our right hand side being minus wi, that is going to be equal to, let's first add the 0th order term. Half of this plus half of this minus this is what? The first term, right? The first term, let's say we have minus 1 onto this, we have half onto this, and half onto this. What's the result? 0, yes. Okay. Now the second term, we have nothing over in wi, but we have half over here, half over here. What's the result? 1? No, but we have a minus here. Again, we have 0, right? How about here? We have half here, and nothing on the top. We have, yeah, this one we actually get something. Times delta x squared, because minus delta x squared is actually delta x squared, plus O delta x cubed, right? Okay, so again, we remember we want to approximate the second derivative with this times some unknown a, right? So basically we want to multiply some unknown a so that this is approximately equal to that, and we already have a term over here. So what should a be? A actually should be the reciprocal of whatever that is here, half of delta x squared, right? So that we are going to cancel the half, cancel the delta x squared, so that we obtain this second order derivative, right? Okay, so that means we have an a that is equal to 2 over delta x squared. Okay, that means we can approximate this with we can cancel this 2 over here, wi plus 1 plus wi minus 1 minus 2 wi divided by delta x squared, right? So I'm basically plugging this into here. We get this. Okay, there is a residual term that is a, which is this, times O delta x cubed. And we know that if this term contains things at least the delta x cubed, it can cancel with this, and the whole thing is going to O delta x, right? Something that shrinks as delta x gets smaller and smaller. So this is a good approximation, right? So when you see we have an approximation whose error actually goes to 0 as delta x goes to 0, it's a good approximation. Or with official terms, it's called a consistent approximation. When you see the error shrinks as delta x goes to 0. So now we have derived our first finite difference scheme, and we can use this to solve our partial differential equation. So we'll continue on Wednesday. All right.